In this lesson for NIOS and CBSE chemistry, we will compare two very important thermodynamic processes, the isothermal process and the adiabatic process. We will build intuition with pictures, write the key formulas, draw the pressure-volume diagram, and finish with short numerical examples you can copy in your exam practice. Let us start with the core ideas. Isothermal means the temperature stays constant. Adiabatic means no heat is exchanged, so Q equals 0. For an ideal gas in an isothermal change, pressure times volume is constant. That is, PV equals constant, or P1V1 equals P2V2. For a reversible adiabatic change of an ideal gas, we use two relations. P times V to the power gamma is constant, and T times V to the power gamma minus 1 is constant, where gamma is the heat capacity ratio Cp over Cv. Now, the energy bookkeeping. For isothermal processes of an ideal gas, internal energy does not change because it depends only on temperature. So delta U equals 0, and the heat absorbed equals the work done by the gas. Q equals W equals N, or T times the natural log of V2 over V1. For adiabatic processes, Q equals 0 by definition, so all energy change shows up in internal energy. Delta U equals negative W, and the work is W equals bracket P 1V1 minus P2V2 bracket, divided by gamma minus 1. Let us visualize both on a pressure-volume diagram. We place volume on the horizontal axis and pressure on the vertical axis. We will draw an isotherm and an adiabat that pass through the same point to compare their slopes. Notice the isothermal curve is a gentler hyperbola, while the adiabatic curve is steeper. For the same increase in volume, pressure drops more quickly on the adiabat than on the isotherm. Let us make it concrete with simple piston pictures. First, isothermal. Imagine a gas syringe immersed in a water bath that keeps the temperature fixed. We pull the pistons slowly, the gas expands, heat flows in from the bath, and temperature stays constant. Now, adiabatic. Imagine a well-insulated cylinder, like wrapped in a thick blanket. We compress the gas quickly. No heat flows in or out. Q equals 0. So the work changes the internal energy and the temperature rises. Let us calculate fast. First, an isothermal expansion example. 1 mole of an ideal gas at 300 Kelvin expands slowly from V1 to V2, where V2 over V1 equals 3. Compute Q equals W equals N, our T natural log of V2 over V1. Now, an adiabatic compression example with a diatomic gas. Take gamma equals 1.4. Start at P1 equals 1 atmosphere, V1 equals 2 liters, compress adiabatically to V2 equals 1 liter. Use PV to the gamma equals constant to find P2 equals P1 times V1 over V2 to the power gamma. Then compute W equals bracket P, 1V1 minus P2V2 bracket divided by gamma minus 1. And convert atmosphere liter to joules using 1 atmosphere liter equals 101.325 joules. Here are the key points to remember for exams. State clearly, isothermal means T constant, adiabatic means Q equals 0. Write the correct relations. PV equals constant versus PV to the gamma equals constant, and TV to the gamma minus 1 equals constant. Mention energy relations. For isothermal, delta U equals 0 and Q equals W. For adiabatic, Q equals 0 and delta U equals negative W. Sketch the pressure-volume diagram. Adiabatic curve is steeper than isothermal.